Furthermore, the ability to predict solar flares with greater accuracy has a direct impact on global communication systems, aviation safety, and the integrity of space missions. As we depend increasingly on technology that is vulnerable to solar activity, the stakes for accurate predictions rise. Enhanced understanding and forecasting mean that astronauts, pilots, and everyday users of mobile and internet services are safer. At the core of every solar flare lies the process of solar magnetic reconnection. This study by Marcel Corchado-Albello, also from CU Boulder, peels back the layers of this complex phenomenon. Solar magnetic reconnection occurs when oppositely directed magnetic field lines on the sun snap and realign, releasing a burst of energy that we observe as solar flares. Using state-of-the-art imaging data from the Solar Dynamics Observatory, Albello's team was able to observe these reconnections in unprecedented detail. Their focus was on identifying quasi-periodic pulsations, which appear as rhythmic fluctuations in the energy output during a flare. These pulsations are akin to a coded message regarding the inner workings of solar flares. The study revealed that these pulsations could provide critical clues about the timing and strength of subsequent solar flares. Understanding these patterns is similar to learning the rhythms of an erratic heartbeat, which could spell the difference between routine monitoring and emergency intervention in space weather management. The detailed insights into quasi-periodic pulsations and their relation to flare energies have profound implications for predicting solar activity. The research opens new avenues for exploring how these magnetic reconnection events can be modeled and predicted. The ultimate goal is to integrate these findings into global space weather prediction models, enhancing our ability to forecast and respond to solar disturbances with precision. As we deepen our understanding of solar phenomena, our insights into magnetic dynamics continue to evolve. One of the fundamental components of these dynamics is the behavior of magnetic flux tubes on the sun's surface. These tubes, which emerge from the solar interior, carry intense magnetic fields. As they reach the sun's surface, these tubes interact, twist, stretch, and reconnect in a dynamic display of solar physics. This interaction is not just a spectacular visual phenomenon. It's also a critical process that releases vast amounts of energy. During magnetic reconnection, which often occurs when these flux tubes meet, the magnetic energy stored within them is transformed into kinetic energy, motion, and thermal energy, heat. This energy conversion is what powers solar flares, which are as potent as millions of hydrogen bombs exploding simultaneously. This process is central to understanding how solar flares develop and how they can be predicted with greater accuracy. By studying the impulsiveness of these solar flares, we gain invaluable insights into the conditions that lead to these explosive events. The intricate dance of magnetic fields during a flare, particularly in the zones where reconnection occurs, is critical for predicting when and how these flares will manifest. Understanding the geometry and speed at which these reconnections occur helps us model the energy transfer from the sun's fiery core to its outer atmosphere. Enhanced predictive models, enriched by recent research into these magnetic flux tubes and quasi-periodic pulsations, are transforming our approach to space weather forecasting. Unlike traditional models, which relied heavily on observations of past solar flare occurrences, the latest models incorporate nuanced details about the energy released during magnetic reconnection. This allows forecasters to predict not only when a solar flare might occur, but also its potential intensity and the likely duration of its impact. The practical applications of these advanced predictive capabilities are vast. For satellite operators, enhanced forecasts mean the ability to implement protective measures that mitigate the risks posed by intense solar radiation. This could include adjusting satellite orbits, powering down sensitive electronics during peak flare activity, or reinforcing satellite shielding in anticipation of severe space weather events. By having a clearer understanding of when a solar storm might hit and its likely intensity, grid operators can enhance the resilience of power systems, ensuring that fluctuations in the geomagnetic field caused by solar flares do not lead to catastrophic failures. Thank you for joining us in this exploration of the sun's fiery secrets. Today's journey through groundbreaking research highlights not just the power of the sun, but our growing ability to predict and protect against its turbulent outbursts.